All right, let's do a brief review about how we defined the cost function, okay, for linear regression problem. Remember, our goal is to predict the price, and we will linear function in the form of theta 0 plus theta 1 times x as our predicted value y hat. Okay, so the theta 0 and the theta 1 are the parameters we want to find. Okay, we want to find the thetas that give us the best predictions. Okay, so in order to define what kind of predictions are the best predictions, we want them to be as close to the ground truth as possible. So we'll use the mean square error as a way to measure this distance between the prediction and the ground truth. It's basically a sum up. We sum up the squares between the squares of distances or the squares of differences between the ground truth yi and the prediction y hat for the ith instance. Okay, and y hat it is computed by the linear model. Okay, so this 1/2m is for convenience for in the future step when we take the derivatives of the cost function. Okay, then the 2 will eliminate with the 2 here. So these are just for the convenience of computation. All right, this is how we define the cost function. And actually last time we already step into the parts for the normal equation method. Okay, so this normal equation method is based on the it's based on the properties of the cost function. The cost function is a quadratic function with respect to theta 0 and theta 1. Okay, and it's relatively easy to find the maximum or the minimum values or the maximum point or the minimum points for a quadratic function. Okay, we can take a derivative of the quadratic function with respect to the variables, right? In the case of our cost function, j, here we can take the derivatives of j with respect to theta 0 and theta 1, respectively. We have two variables, two unknown variables, and we can treat them as, we can treat the other one, like when we are computing the derivatives of with respect to theta 0, then theta 1 is a constant, okay? And how we compute the derivatives for theta 0 and 1 are here. So from this step to the step in the dash line box, there's some steps that I omitted, but basically these can be solved, okay? By solving these two equations. Let me use another color. Solving the two equations in the box, we can basically find the theta 0 and theta 1 as our solutions.
We have to know the math to do that.
Echo. Okay.
Will we have to know the math to do that? Like the steps in between?
No.
Okay.
Because I have put the solutions on next page. The mathematical details here are basically not that advanced techniques, because if you observe theta 0, theta 1, theta 0, and theta 1, these are just the linear equations. Okay, you can basically eliminate same terms by manipulating the coefficients. So we can obtain the solutions to theta 0 and theta 1 quite easily, which are in this form, okay? And if you look at the solutions, we have some simplified notations. For example, a little bar above y, which is y let's call it y bar. Okay, so the y bar is the mean values of all y's. Okay, and y is the ground truth, is the actual price, and x is the mean values for all the inputs features, which is in this case is the size of the house. Okay, and the θ1 is computed in this way, which is a relatively complex, more complex form. And if you are familiar with linear algebra, you will see this term quite. It's just exactly the term for how we define the covariance between two variables, y and x. And this summation, the denominator term, xi minus y bar, xi minus y bar, minus x bar is the deviation from the mean values. So the summation of the denominator is the summation of variance. So θ1 and θ0 can be obtained by solving the linear equations, and we are happy about this because that's what we want, right? Given the θ0 and θ1 solved, we're able to make predictions. Okay, so we're all very happy about that. And before we went into the next step of looking at more complex models, we will have a little peek of how we evaluate the models. Okay, so this is not a systematic introduction to evaluation techniques in machine learning, but it's just for linear regression models. Okay, so for evaluating the model that we just obtained, we can use the difference between the ground truths and the predictions, y hats. Okay, so if we use this difference, if we directly use ground truth minus y hats, which gives us the error term, and this error term is basically the difference here indicated by the green, the yellow, the red vertical lines. But this summation of error terms is always 0 because the y hats can be computed by this way. And if you use θ0 to substitute into this term, then you can basically find this error term. If you sum up the error term, it will sum up to 0. So the absolute values of errors are more useful than the actual values of error itself. So anyway, but this is not an important part because for the next lecture, we will have a more systematic review of how models are evaluated in machine learning, for machine learning models, not just for regression models. And just a little bit knowledge for other evaluation metrics. For example, R-square. It measures a proportion of variance in the target variable that is predicted from yi. And this R-square, it's commonly used metrics because it tells how good a linear model is in terms of how much interpretability, how much variance it can interpret. Okay, we want this value to be as high as possible, and it is always between 0 and 1. Okay, so the R-square is basically computed from the ratio of sum of squares. Okay, if you compute the total sum of squares using the ground truth y and the y hat and the y bar, and the residual sum of squares, which is the difference between the ground truth and the predictions, and use the ratio between these two sum of squares, you are able to predict, you are able to compute R-square. And again, this is not the focus of this course, but as a practice, we will have a have a question, a small question in the next assignments in Jupyter Notebook, how you compute this sum of squares, and for computing the residuals. So yeah, I think, and it's also a good way to practice NumPy usage in general. Okay. So the last piece for the evaluation part is you can plot the residual or the error terms, EI, okay, against the predicted values. Okay, and basically we want the residuals are evenly distributed along predicted values, so that the linear regression, so that the model fits the linear assumption better. Because the assumption is that the data, they follow a linear principle. It's not a nonlinear function. But it's also very common to observe that the residual plots is not evenly distributed. And in this case, if it is not, then it indicates that there could be some better models than linear models. Okay, so these 3 slides that we have just shown are a brief review, a very simple review of statistical techniques for evaluating linear regression models, which I believe they are mainly a summarized a little bit about the statistical models. So let's proceed on to the next parts to look at the case that we have more than 1 features. Okay, so just look at the model we just learned again. We have theta 0 and theta 1. Okay, and the meaningful feature is just 1 feature, which is the size, right? But we need to include theta 0 as an intercept term so that the model is more comprehensive, right? So in the case of more features, say we have the year, the house year as a 2nd feature, then you can imagine that we need to have a theta 2 as a 3rd parameter. And if we have number of rooms as the 3rd feature, then we need to have theta 4, right? Theta 3 actually. So let's look at how we do that in practice. Okay, and let me stop sharing for now and start playing the slides quickly. And share the screen again. You guys can see it clearly, right?
Yes, it's full screen.
Okay. Great. Yeah. So more features means we need to have more parameters to take the information from that feature into our model. Okay. So in this case, we added the year, the location as the 2nd and the 3rd feature. Okay. And now to present the data, if we look at the first 4 columns, we have these 3 columns are features, are actual feature. And the first column is kind of a artificial column or a pseudo column. It's the intercept column. And the values for this column are all 1s. And these are just for the convenience for fitting the parameters, because there's a parameter theta 0 that we need to fit. So we can imagine that there is this intercept column that have all 1s, okay? And the labels is here, it doesn't change. So in order to fit a model that has more parameters, we just extend the model by sum up the linear combinations in this form. Previously, we only have theta 0 plus theta 2 theta 1 times x1. And now we have more features, and then we need to include the other 2 additional linear terms. Okay, and we simply use this longer term to predict y. And let's see what kind of results we will have. Okay, so going back to the mind model for machine learning models here, we simply have a longer feature or a longer parameter vector here. So previously we just have theta 0 and theta 1, but now we have theta 0 to theta n, which is a longer column vectors now. Okay, and in statistics we call it a multiple linear regression. And this multiple is simply for we have multiple input predictors, we have multiple features. Okay, with each input predictor, we will have a corresponding parameter. So we will have n+1 parameters in total. All right, but the goal is not, the goal is the same. We want to learn a function that predicts from x to predict y. Okay, so the form of the function is like this, right? And the predicted value is y hats. Okay, if you write it in this way, y hats. Okay, and the cost function is the same. It is the mean square error term between the y and the y hats. Okay, the cost function, if you write it still using the j notation. Okay, and also include this theta 0 to theta n as the inputs, and we have yi minus y hats. Okay, so all the remaining terms, they represent y hats. Okay, and raised to the power of 2. Okay, so since now we have n features, which is n+1 parameters from theta 0 to theta n, then it seems not that practical if we want to expand this whole long mathematical equations, very long mathematical expressions. Okay, so we will use the tool for matrix representations instead of writing each terms out. Okay, so oh, by the way, I have uploaded a external link to a refresher for linear algebra and the calculus. It's a part of the course material from Stanford's CS229 machine learning course. I think it's a very famous material, and some of the reviews in that link are not just useful for linear regression and logistic regression models that we will learn for now, but also will be useful for the more advanced chapters that we will cover in the remainder part of this semester. Okay, like PCA, like clustering. I think these are all useful materials.
And where can that be found on Canvas?
Yeah, it's already uploaded to the current module, to the linear regression module. All right. So for long mathematical expressions, we will need to use the matrix representations for the convenience of write all these notations and to compose meaningful computations. And I would say we want to represent the computation in a compact form rather than writing down all the mathematical terms. Okay, so what we will do is to use a matrix in capital letter X in capital letter, which has m rows and n plus columns to indicate the data. Okay, and the Y, the label, also has m rows, but with just one column. Okay, so if we look at it, it'll be like this. If we draw the first row, right, it's from 1 to x1, x2, xn with superscript 1 in the round brackets. So the superscript is for the to indicate that instance, because the first row is one data instance or data example, and second row with superscript equals 2, and the mth row, the last row, is the mth data example. That's x, okay, and that's y we have, okay. And also, together with data, we can represent the parameter, model parameters, theta, with a theta in bold, okay. The bold theta means it's a vector. It has n+1 rows and 1 column. It's a long column vector, okay. So use the matrix representation, we can represent the cost function in a very compact form, okay. We can first compute the predicted value basically by multiply the matrix X with the vector theta. Okay. If you put the two together, you will have X here, oops, X in the middle, that's X. It's a m by n+1 column, m row by n+1 column matrix. And this is our theta. And on the left, it's y hat. Okay. So I will do a brief explanation for the principle of matrix multiplication. Okay. So in order to do the matrix multiplication, you need to first check if they are compatible. So in this case, we are multiplying x with theta. The condition of compatibility is that the number of columns of x should match the number of rows in theta. And indeed, they match, right? They are the same, they have the same value. Okay, so what this matrix multiplication does is to take the first row of x and compute the dot product with this first row with the theta vector, okay? And the dot product is theta 0 times 1 plus theta 1 times x1 plus theta 2 times x2 until theta n times xn, okay? And that will give us y hat 1, okay? If you write it on your own paper, you will find the one-to-one mapping relationship because the number of columns matches the number of rows, okay? So that's how we get y hat, which is the predicted values. So note that the y hat is now also a vector. It's no longer a scalar number. It's a long vector now, okay? All right, that's how we represent y hat. And after y hat is represented with a vector, we're able to represent the cost function also with the vectors form, with the matrix representations. Okay, so this step may be a little not that intuitive if you haven't practiced matrix vector dot product for a long time, but it's also understandable because if you look at the y and the y hats, let me use a two color. If you look at, so let's look at first, look at y minus y hats. Okay, so y has m plus 1. Actually m columns, m rows. Okay, so y is a long column vector, and y hat is the same dimension. It also has m rows. So if you use y minus y hats, the results will also be a long vector like this, right? And in each row, it'll be y1, 1 in superscripts minus y hat 1, right? That'll be the first column, until y m minus y hats m, okay? Okay, and the transcript symbol T here is simply to put this long vertical column vector to lay down that vector to make it a horizontal long vector. So this blue part becomes a long horizontal vector which has the same element in it, which is y1 minus y1 hat, okay, until y m times minus y hat m. Okay, so that's how you get the row vector. So then we are multiplying the two vectors together, and this multiplication is actually a dot product. Okay, and the dot product means that we take the first element times the first element here, sums with the second element times the second element times the last element times the last element. Okay, so which will basically give us the form of mean square errors, but which is in a much more compact format. Okay, all right. So we'll have the form of cost function j of theta in a very compact format. And now let's, if you write it with a more, by expanding it, by substitutes the term for y hats from the previous slide, right? Remember, within for the previous slide, we defined how y hat is computed. It's simply the dot product between x and theta, or the matrix multiplication between x and theta. Okay, so we substitute it into the form, into the expression, into the equation for j. It will give us this. Okay, so now if we apply some the principles of linear algebra by moving the transpose symbol into the brackets, we move the transpose t into here, right? Inside the brackets, it will give us some more convenience of like some transformation of all the terms. Okay, so it's like a binary term in if we think of y and x as scalar numbers. So similar rules applies. So we have y transpose minus x theta transpose times y minus x theta. Okay, so if we expand the term, it becomes y theta times y, x theta transpose times I, y transpose times x theta, and x theta transpose times x theta. Okay, so it's similar to the same algebra principles that we apply if x and theta are just numbers. Okay, so we can merge the same term, right? Merge the two terms here. It's basic, and do the further move the transpose symbols around. Okay, so it will give us something like this.
Yeah, so how did you merge like y transpose with just a y by itself? Like how are they the same term? So you have two in the middle underlined in red that are same term, but the y transpose and the y are not identical. Or is it the, yeah.
Yeah, so this is y transpose times y. It's just one term.
Right, no, so the two middle terms, like how do you merge them into one term when you have a transpose and you have, like the transposes are opposite?
Yeah, so it's basically, if you look at the nature of of x theta transpose. So x theta is just a y hat, right? X times theta is just y hat. It's just a long variable. It's just a long vector from this step. Okay, so the results of so let me use the different color here. So this first term, it's basically y hat transpose times y, right? And the second term, it's basically y transpose times y hat. Okay, we just exchange the order of multiplication, but doesn't change their values. So these two actually have the same same elements or same values, actually. Because y hats transpose will be y hats 1, y hats 2, until y hats m, right? It's a very long row vector, and the y is a column vector, which is from y1, y2, until yn, right? So if we are computing this term, y hat transpose times y, it should be like this, right? And on the other hand, if we compute y transpose, then it is y1, y2, and yn. It's a row vector now, and y hat is a column vector. And y hat 1, y hat 2, and y hat n, right? But the results of these two dot product, they are the same because we are basically doing the same. It's y hat 1 times y1, y hat 2 times y2, plus ym times y hat m times ym. And the dot products above here is the same operations involved. So the results would be the same for y hat transpose times y or y transpose times y hat.
So can you go forward one partial slide?
Mm-hmm. In the previous slide, you mean?
No, right here at the bottom. Yeah.
Yeah. Okay. Yeah.
So how did you decide that it would be x theta transpose as opposed to x theta and then not transpose y transpose? Or is that just kind of irrelevant?
It's irrelevant. It's irrelevant.
Okay, cool. Thanks.
Yeah, that's totally irrelevant. Yeah. Yeah. Now let me clear the slide. So now the final term looks pretty much like a quadratic function. If you think of the y as unknown variables, it looks very like a quadratic function, right? But the thing is that we want to take the derivative of j with respect to theta, because y and x, they are all known. They are from the data, right? We know everything about the data, but we don't know about theta. We want to know the theta that's minimize the cost function. Yeah, that's what we want. So we will do something with respect to this cost function, okay? So given this cost function, we need to compute the derivatives of this cost function with respect to the theta, okay? Because theta is the unknown variable. Okay. So the j is like this. I just copy the j from the previous slide to here. And there's no theta in this, oops. There's no theta in the first term, so it'll be gone, right? It's treated as constant. And there is a theta here, right? So we'll keep it, And there's a theta in here, so we'll keep it, okay? So the derivatives of j with respect to theta is the derivatives of these parts plus the derivatives of these parts. Yeah, that's simply the rule of computing derivatives. Okay, and from these step, from these step to this step, on this slide, I didn't show all the details, because if you want to know how, then it basically involves a lot of basic linear algebra knowledge. But the strategy we take is to use the analogy to scalar numbers. So if we have x and y as one-dimensional variables, not matrix or vectors, if we want to take the derivative of theta times x times y with respect to theta, and the result will be simply x and y, right? If we take the derivatives with respect to theta square times x square with respect to theta, and the result will be 2 x squared times theta. So this is the realm for scalar numbers. And actually the same principles applies to matrix and the vector multiplications as well. So the similarity is here, the theta is here, and the theta transpose times theta, you can think of this theta as the quadratic terms, okay? So taking the derivatives of these two will result in this, okay? Which is minus 2x transpose times y plus 2x transpose times x theta equals 0, okay? So because we want it to be 0, we want to find the minimal points, and then we are able to solve theta.
So why is the theta transpose disappearing, not the theta?
And of course, you can put it y theta. Then you need to write it as theta transpose and x times x transpose. And these two are equivalent. It's also irrelevant because theta and the theta transpose is just the two representations of the same vector. Theta is a column vector, and the x theta and the theta transpose is a row vector. It is just different ways of putting the presenting the elements.
So okay. Then when there's the theta transpose and the theta in the same one, is it very similar to like a theta squared?
Yeah, it's similar to theta squared. Yeah.
Okay, thanks.
Yeah. Wait, what is the derivative of transpose variable? So now we're talking about the derivatives of a vector, right? I see the question for derivatives. So that involves actually quite a lot of chapters to describe that. So to put it simple, if we want to know the partial derivatives with respect to a vector, in this case, theta is a vector, right? So what we basically need to do is to take each element in that vector out. For example, we have theta 0 and theta 1 until theta n, right? Because that's all the parameters we have. And theta alone is a long vector, okay? So in order to compute that, we need to do this. We need to compute the partial derivative of j with respect to theta 0. That's our first component. And the second component is the derivative of j with respect to theta 1. And until the last component, which is the derivative of j with respect to theta n, okay? So that's what we need to do, okay? But that's too much if we put all the details here into one slide. There's no way to do that. So we simply use this simplified notation of theta rather than writing out all the components of it. Okay. So in order to solve it, right, we have an equation here. If we move these to the right and eliminate the 2's, we will have this equation, and we can solve theta by times the inverse of this matrix on two sides. Okay, so the meaning of the inverse is that if you times a matrix with its inverse, it will give you a identity matrix, which means there's only ones along the diagonal lines, and all the other items are zeros. Okay, so that's also the linear algebra knowledge that need to, if you really want to understand details, you really need to have a review of. Okay, But here, that's not a point for our purpose. Here, our purpose is to find the solution for theta, and times the inverse for the matrix X transpose times X will give us the solution here. Okay. All right. And this is actually a very compact form of solutions. Because if you think of the solutions for the simple linear model case, which only has one feature, we need to compute theta 0 and theta 1, which is already a pretty complex forms. And now we have more features involved than if we write all components of theta individually as mathematical expression. That will be insanely complex. So, but if we use the matrix representation, things will be much easier. Okay, we can just use the transpose and inverse of matrices to indicate one solution. Okay. All right. So for more details, if you follow, I hope this link still works. You will see an example with more details information. All right. Okay, so what we called a normal equation solution is just this solution. Okay, by normal equation solution, we use this. We are actually referring to this solution. Okay, so given the data X, given the data Y, we are able to compute the solutions to a linear regression model in a very straightforward manner. Okay. Oh, at least it looks like so. Okay. Although there's a lot of computation going on when we compute the transpose and the inverse. Okay. We'll see how practical this method is in actual in the next slide. Okay. Okay. So some tips for computing the derivatives, right? I think I mentioned these parts. I just manually wrote something down here. So the derivative of a function with respect to a vector is something that you need to take each element out of that vector and then take the derivative for that component. So the resulting derivative is actually the same dimension as theta. If theta is three-dimensional, it has theta 0, theta 1, and theta 2. And then that means the derivative of J with respect to theta is also three-dimensional. Okay, it's just theta 0, theta 1, and theta 2. Okay, so the dimensions always match between these two between these two quantities. So we can use this to check whether our computation is correct or not. Okay, so for example, the dimension for theta is n plus 1 by 1, right? Because we assume there are n features. And the dimensions for y is m by 1 column vector, okay? And the dimension of x is m by n plus 1, okay? So given this information, okay, and also the cost function is a scalar number, which means it's just one number. It's a 1 by 1 quantity. We can use this information to check whether our solution is correct or not. Okay, by looking at by using the principles of matrix multiplication. So if we want to find the dimensions of this term, we are actually multiplying x transpose times x, right? And x transpose is n plus 1 by n, because we know the x is n by n plus 1. And x is here. So the n matches here, which means this is valid, right? And the results of x transpose times x is n plus 1 by n plus 1. and the inverse of it doesn't change the dimensions. So this n plus 1 also matches this n plus 1. Okay. And here, this m also matches this m. Okay. So the result would be a n plus 1 by 1. On the right, the result would be n plus 1 by 1. And on the left, it's also n plus 1 by 1. So the two sides meet, okay, which means our solution is correct. And this is a quite commonly used technique to examine whether your computation is correct or not, if there are a lot of matrix and vector computation involved in your solution. So it's very useful when you want to quickly check if there are any error in your mathematics, in your math, or in your code. All right. So let's go back to the model. The normal equation solution gives us a very convenient way to directly obtain a solution from data. Okay, given x and y, we're able to instantly get, seemingly instantly get a theta. Okay, but this method has its own issue. Okay, and the biggest issue is that if there's very small number of features, say there's only one feature, okay, then it's very fast to compute, right? Because there's just very little computation involved, okay? However, if we have a lot of features, then we need to compute the inverse of a matrix that is n plus 1 by n plus 1 dimension, okay? Which is really expensive, okay? If you look at the dimensionality of this matrix inside, which is n plus 1 by n times m by n plus 1. Okay, so the result will be n plus 1 by n plus 1 matrix. If you want to compute the inverse of that matrix when n is big, then the whole computation is really expensive. It'll take a very long time to compute. And the results will be returned. You need to wait for a long time before the results come out. Okay, so basically, we want to have some methods that help us find the solution better, and the solution might not be a 100% accurate result, but it could be an estimate that is good enough. Okay, so in theory, the normal equation method should give us the theoretically best solution. Okay, so it should give us the solution, the thetas that's minimize the cost function into the theoretical minimal points. But in practice, we don't actually need that accurate estimation. We just as long as the thetas approach the minimum points as close as possible, then we're pretty happy about that. Okay, so that's why we will introduce the second method, which is called gradient descent. Okay, or some before the gradient descent, the term gradient descent becomes popular in recent years as deep learning develops. The method has been there in mathematics for a while. People usually call it the gradient method. Okay, so let's look at this method. So to put it simple, it's a iterative optimization algorithm that helps you to find the minimum of a function. Okay, we want to find the minimum point of a function. In the case of our cost function, then the general thoughts of gradient descent is that we will start with an initial candidate, okay? And then we will gradually approach the minimum, okay? And it's a pretty straightforward thought because we don't know, we don't know where exactly the solution is. We don't know where exactly the minimum point is. So we need to start somewhere, but we will gradually approach the minimum point using some ways to find the directions that points to the minimum points. Okay. So gradients, it's almost the partial derivatives that we talk about in calculus. So partial derivatives means that it's a derivatives with respect to part of the variables, right? We have when we have a lot of variables altogether, then if we compute the derivatives with respect to just one of them, then it's a partial derivatives, okay? So in a case for, in our case, when our thetas have a lot of components, we have theta 0 to theta n, then if we want to compute the derivative of cost function with respect to theta 0, then it's the partial derivative. It's not a complete derivative. Oops, okay. And the term derivative is defined on single variables. So that's basically the difference here, okay? If we use the derivative, we can write it as using these mathematical forms, okay? But the gradients is defined on functions of multiple variables. So in multiple variables, the gradients, we can write it as this upside down triangle here to indicate this is the gradients with respect to a vector, okay? But so far, I mean, throughout the whole course, we'll basically use the derivatives with respect to each component in such a format, okay? So they basically are the same concept, but applies to different target variables. Anyway, so the derivative, what it measures is how much the outputs will change if the input changes a little bit, right? That's the basic meaning of derivative. It measures the sensitivity of the output with respect to the input. So in the case for a linear line or a linear model, then the derivative shown here in this plot is the ratio of the change of y over the change of x when that change is approaching to the very small value, right? That's how we measure the slope of the linear model, okay? And that concept applies to nonlinear functions as well, right? So given this quadratic function, it looks like quadratic function. So if we draw this line across the point of x, we will find the new points x plus h and the new y value x plus h, f of x plus h. So if we compute the limits of this quantity when h approaches 0, it'll give us the estimates for the derivatives near the point of x, okay? So that's the nonlinear case. And more interestingly, we can apply the same concept to a two-dimensional or multiple variable case, okay? So if we have a function that takes two variables as inputs, we can compute the gradients of this function by computing the partial derivatives with respect to each variables, okay? So if you look at the blue arrows here, they actually point to the direction of the gradients, okay? Because the gradients is a vector now. All right. So what the gradient algorithm, the gradient descent algorithm does is to use the gradients, use the direction of the gradients to guide our iterative algorithm to find the minimal points of an algorithm or of a function. So because gradients is a vector and it always points to the direction of the fastest increase of a function. Okay, so if we go opposites of the gradients points to the direction, then we are actually going towards the direction of fastest decrease, right? So we want to go to the minimum points of the function. So it makes sense if we follow the direction that points to the fast decrease of the current points, right? So that's our basic principle of gradient descent algorithm, okay? And our goal is to find the minimum of our cost function, j of theta, and theta is a vector. So we will start from somewhere, which we indicate as theta 0, okay? But we don't know if it is a minimum or not, and it's more likely that it is not. So then we will choose a direction to change theta 0 a little bit to theta 1, okay? So remember that here, theta 0 and 1, they are in the superscript. They are not in the subscript. They don't indicate the first parameter or the second parameter, but indicates the iterations of our algorithm, okay? So the theta 0 means this is the initial iteration. Then within the first iteration, we will change theta 0 a little bit to theta 1, so that the j of theta 1 will decrease a little bit from j of theta 0, okay? And we need to choose a direction along which the j of theta that decreases fastest, because this is the most efficient way. This is the most efficient way to find our solution. Okay. And the third step is to repeat the following step until the cost function no longer decreases significantly. Then the final cost function, j of theta n, is the minimum that we want to find. Okay, so I think it's a very straightforward method. We don't have any information, so we'll start from some points. And in each step, we will change that theta a little bit so that the j will decrease a little bit. But in order to choose that direction of change, we need to follow the opposites of gradient points, the opposites of the direction of gradients. And we will repeat the step until we have reached some minimum points, until we are happy with about the cost functions. Okay, so far, any questions about the gradients and the general general idea of gradient descent algorithms? Okay, no question.
Professor?
Yes.
Are these contents available in textbook?
Yeah.
The one you mentioned, like MIT Press one?
Uh-huh.
Okay.
So you mean, is a question that can we find all these materials in the MIT book?
Yeah.
I think so. I didn't read that book a lot, but I think the gradient descent can be found in it.
Okay, thank you.
Yeah. Okay. Now let's take a further step. Okay. Now, so let's use a one-dimensional case to indicate the gradient descent algorithm. Okay. So it's a quadratic function within that takes only theta, and theta is just a one-dimensional variable. It's not a vector here. Okay. So we want to find the minimum points of this quadratic function j of theta. right? Say we start from somewhere, in which case it's theta 0, right? And if we compute the gradients or the derivative at this point, because it's decreasing, right? So the gradients should be negative numbers in this point. So the gradients actually points to left, point to the right, because the gradients is the direction where the function increases, okay? So all we need to do is to go opposite against the direction, okay? We need to move towards the opposite direction by a little step. And this little step is determined by something called a learning rate alpha, okay? So how big a step we take at each step of gradient descent is partially determined by the gradients and the learning rate alpha, okay? We will let theta 1, so this 1 means the next iteration, okay? Theta 1 be theta 0 minus alpha times the derivative of j with respect to theta 0. This minus is important because we're going going against the direction of gradients, okay? So that's how we get theta 1. The black arrow points to the opposite direction of gradients. That's where we are moving towards, okay? So theta 1 is here, so we are moving downwards a little bit, and we have a new theta 1, right? And we find that as long as alpha is smaller enough, then theta 1 will be closer to the minimum rather than theta 0, okay? As you see that theta, the alpha cannot be too large. If alpha is too large, then we'll go too big a step, right? We maybe go beyond the minimum points, okay? So it'll be better if we be a little bit conservative at the beginning, okay? So from the plot, we can see that the values of the cost function indeed decreases, okay? J of theta 1 is smaller, indeed smaller than J of theta 0. All right, that's one iteration of the gradient descent algorithm. So what do we do next? We simply repeat until a satisfactory theta n is reached, right? For example, in the next iteration, we find theta 2, which has even smaller cost function values, and then theta 3, right? So that's basically how we conduct gradient descent in a 1D scenario. So in the let's look at how the different initial positions may influence the outcome of the gradient descent. Okay, because in the previous example we show a picture that we start from the left of the minimum point. So we'll see that if we start from minimum from the right of the minimum points, the general principle doesn't change. And in this case, the initial gradient is greater than 0, okay, because it's increasing. So we should go towards left, which is the opposite of the gradient, okay, which give us theta 1, okay. So as a result, theta 1 is smaller than theta 0, and if the step is smaller enough, we'll have J of theta 1 much smaller than J of theta 0. Okay, that's one iteration done. All right, and we will eventually reach the minimum points if we controlled all the parameters in the carefully. Okay, don't go too much step. Don't go too big. Don't go by a too big a step. Right, that's the most important thing. So no matter where the initial point is, the principle is basically to move to the opposite direction of gradients. Okay, that's something we can show with this one-dimensional gradient descent algorithm. Okay, then let's look at the two-dimensional demo for gradient descent. If we have J of theta 0 and 1, we have two variables now, right? Suppose that's where we start, okay? Then in the first iteration, we need to compute the gradients. And remember that now the gradients is a vector. Okay, it's the partial derivatives of J with respect to the first component, 0 and 1. Okay, so the zeros in the superscript, they refer to the first iteration. Okay, all right, so suppose that's where the direction, where the gradients points to. Okay, in the 2D space. Okay, now we need to move towards the opposite of the gradients, and that's the opposite side of the opposite direction of the gradients. Okay, so we'll basically use the alpha minus alpha times the gradients, similar to the 1D dimensional case. Okay, so the new theta will be here. Okay, with 1 in the superscripts to indicate the iteration. And in the iteration 2, we'll do the same thing, which finds newer points, right? And theta 3, until we reach some points that we are pretty happy with about the cost function. All right. Let's summarize a little bit. Summarize the gradient descent a little bit. So we will start with some initial values for theta 0 and repeat until we are satisfied for the following steps. First, we will compute the gradients of J at the current iteration, and then use it to update the parameter. Okay, so the theta of the next iteration will be the theta of the current iteration minus the gradients of the current iteration times by alpha. Okay, and we are done with the current step. And until we are happy about the cost function, then we can obtain the final parameters. Okay. All right. So I think I will stop here. We have talked about the normal equation methods and the gradient descent methods in general. So gradient descent methods are covered in general. So in the next lecture for linear regression, we will finish the parts for the gradient descents for linear regression. And we will release the homework for linear regression models later today. Yeah, because you can already start working on the normal equation part. All right.
Then will there be a quiz on today's material?
Yes, there will be a quiz. Okay. Yeah, yeah. The first homework will be due in 3 days, this Friday. And the new homework will also be due next Friday. Yeah. I usually use Friday as the due date for each homework. Yeah, so you will get roughly a week, usually more than a week to finish each homework. Yeah, it's another Jupyter Notebook homework. I will release homework later this evening. Yeah, after I have uploaded everything, uploaded the video stuff.
Will future homeworks be like homework 1, where they have like what the expected output is?
You mean for the linear regression homework?
Well, just the ones that are moving forward. So homework 1 has what example solutions look like. Will the other homeworks in Jupyter Notebook have expected outputs? Does that make sense?
Yes. So basically all homeworks will be in that style. I will.
Excellent. Thank you.
Mm-hmm. Yeah, all homework are basically Jupyter Notebook. Okay, thank you guys. So good to see you here, and have a good day. I will see you on Thursday's meeting.
Okay, thank you, Professor.
Thank you.
Bye.
Thank you, Professor. Stay safe.
Stay safe.